Hi everyone, in this video we will discuss exploratory factor analysis, also called EFA, and how to conduct this analysis using SPSS. First, let's differentiate between EFA and CFA, or confirmatory factor analysis. Factor analysis is a method of detecting underlying factors among variables. The variables we use in the survey are called observed variables, and the factors derived from the factor analysis are called latent variables or constructs, also factors. Confirmatory factor analysis is a theory-driven method in which we use ground theories and or literature review to develop a theoretical factor structure. Then we test this factor structure using the collected data to confirm its validity. This method will be covered in DAV 724. Exploratory factor analysis is a data-driven process and exploratory in its nature. There is no ground theories or literature to develop a factor structure. Instead, we use software such as SPSS to detect underlying factors from the data. So the factor structure is dependent on the data. It is recommended that a CFA could be done following EFA to confirm the factor structure derived from the data. In this example, we will run EFA with each bad dataset. Before we run the EFA, we need to test the assumptions. Note that EFA has different assumptions compared to multiple regression, ANOVA or MANOVA. We need to have metric variables, large enough sample size, and homogeneous sample. One important assumption for EFA is intercorrelation among variables. In other words, in order to detect underlying factors among variables, they should be intercorrelated. To run EFA, we go to Analyze in the menu, select Dimension Reduction, and then choose Factor. Note that factor analysis is considered a dimension reduction method, and that is why we select this option. First, we are testing the assumption, then we will run the factor analysis. We will add variables x6 to x18 to the variables box. Then select descriptives. Some important boxes must be checked. KMO and Bayes test of sphericity, which tests the overall intercorrelation of the variables. Anti-image, which shows the individual MSA test. MSA stands for Measure of Sampling Adequacy for each variable. Click Continue. Since we're not running the EFA at this time, we will not select any other options in extractions or rotation. We will do that later. Click OK. Let's examine the output. For KMO and Bayes test, we have two values. KMO, or also called Kaiser-Meyer-Orkin measure of sampling adequacy test, and Bayes test of sphericity. These tests evaluate the overall intercorrelation among variables to see whether EFA is an appropriate method. We expect KMO MSA being greater than 0.5. In this case, we have KMO of 0.609, which is good. We also expect Bayes test being significant. In this example, we have a significant Bayes test. Thus, the overall intercorrelation requirements is met. Then we examine the anti-image matrices to evaluate individual MSA for each variable. We expect MSA value for each variable being greater than 0.5. That is value in the diagonal. We can see that x6 to x10 have good MSA values. MSA for x11 is 0.448, which does not meet the requirement. We will continue to examine MSA for all variables and find that x15 and x17 also have MSA less than 0.5. Thus, x11, x15, and x17 have a low MSA value and they need to be dealt with. These low values mean that these variables do not have a high enough correlation with other variables and might not belong to any factors. The rule of thumb is to remove the variable with the lowest MSA first, in this case x15, and rerun the analysis. So we will do this one at a time. We go back to factor analysis, remove variable x15, and rerun the factor analysis. Here is the output. KMO and balance test still look good. We will examine the anti-image matrices and see that X11 still has a low MSA, which is 0.449, and X17 has a MSA of 0.444. So X17 has the lowest MSA, and we will remove it from the list of variables, and we'll run the analysis again. Basically, we just repeat the steps as before. Again, KMO and balance test still look good. Let's look at the anti-image matrices. In this case, all MSAs are greater than 0.5. Through this example, we can see that as we remove one variable, this will change the MSA of all other variables. And that is why we need to do it one at a time. Now we made this assumption and we can run the EFA. We go back to factor analysis. In descriptives, we do not need KMO and balance test and anti-image anymore, so we uncheck them. The next option is extraction, which indicates the method of extracting factors from the data. Method option lists a number of factor extraction methods. The textbook explains two major extraction methods: principal components and common factor analysis. Principal component analysis considers the total variance and drives factors that contain small proportions of unique variance and error variance. On the contrary, common factor analysis considers only the common or shared variance, assuming that both the unique and error variance are not of interest in defining the structure of the variables. Principal component analysis seems to be most appropriate when data reduction is a primary concern, focusing on the minimum number of factors needed to account for the maximum portion of the total variance. On the other hand, common factor analysis is the most appropriate when the primary objective is to identify the latent dimensions or constructs. The textbook provides more detailed comparisons between these methods. In theory, common factor analysis seems to be more appropriate for identifying underlying factors or constructs among variables. In reality, in most applications, both methods end up with very similar results in many cases. Given the common factor analysis has more restrictive assumptions and is much harder to interpret, many studies use principal component analysis for the EFA purpose. In our example, we will use the principal component analysis, so I will select this option. We also check unrotated factor solution and squeeze plot. We will use eigenvalue of 1 as the method to identify the number of factors. You can also specify the number of factors for the EFA. I would suggest starting with eigenvalue first, and then click continue. The next option is rotation. Typically, unrotated method does not show clear factors, so rotation is needed. There are two major methods of factor rotation: orthogonal factor rotation and oblique factor rotation. With orthogonal rotation, factors are extracted so that their axes are maintained at 90 degrees. Each factor is independent of all other factors. With oblique rotation, factors are extracted so that they are correlated. The oblique method provides information about the extent to which the factors are actually correlated with each other. Typically, if we expect to test the relationship amongst extracted factors, oblique rotation should be used. On the other hand, if we expect these factors are independent, then orthogonal rotation should be used. In practice, it is common to see studies using orthogonal rotation even if the expect factors are correlated. The reason is that some software applications do not offer oblique rotation methods. Additionally, oblique rotation results are harder to interpret. In this example, we'll use both methods and then compare the results. First, let's use the orthogonal rotation. Varimax is the most popular and superior orthogonal method, since it focuses on simplifying the column in a factor matrix and can achieve a simplified factor structure. So we check Varimax, check rotate the solution, and click continue. Next, click options. Since we do not have missing values in this data set, we do not have to worry about that. We need to check subspress small coefficients to avoid showing low factor loadings in the matrix. The recommended value for factor loadings is 0.7 or more, indicating good factor loadings. Factor loadings greater than 0.5 are considered acceptable. Thus, in this example, we will set the threshold at 0.5, meaning that any factor loadings less than 0.5 will not show up in the matrix. Click continue and OK. Let's examine the output. We'll look at the total variance extracted first. We can see that with eigenvalue of 1, we have 4 factors. The total cumulative variance extracted is 79.6%. Note that this total variance extracted is the same for both unrotated and rotated solutions. However, we can see the variance percentage of each factor is different. With Varimax rotation, the first factor accounts for 26.3% of the variance. Factor 2 is 20.3%. Factor 3 is 16.9%. And factor 4 is 16.1%. This distribution is much more even compared to the distribution with unrotated solution. We can also examine the scree plot. The key to use scree plot is to determine the number of factors is to find the elbow of the plot. In other words, we look for the point where the slope has a sudden change. In this example, the elbow indicates 5 factors. With 5 factors, the eigenvalue is less than 1 and it only increases the total variance by 5%. So we'll stick it 4 factors as suggested by the eigenvalue. Next, we look at the component matrix. Component matrix shows unrotated solution with factor loadings greater than or equal to 0.5. We can see that the factor structure is not very good here, where factor 1 with 4 items, factor 2 with 5 items, factor 3 with 2 items, and factor 4 has only 1 item. We'll examine the rotated solution for a better factor structure. We can see that we have a better distributed factor structure. Note that most factor loadings are greater than 0.7. We have an issue with X11, which shows factor loadings less than 0.7 in 2 different factors, factor 1 and factor 4. This is a case of cross-factor loading, a situation in which an item could be attributed to more than one factor. If you remember at the beginning when we examined the MSA, X11 had a lower MSA than other. One solution is to remove the item from the analysis. If we have a limited number of variables and have good rationale to keep the variable, then we have to make the case to keep it. In this example, we will remove this variable. So we go back to the factor analysis and remove X11 from the variable list and run the analysis again. Let's examine the output. We still have 4 factors. And here's the rotated solution, which shows great factor loadings and a clear factor structure. Factor 1 has 3 items. Factor 2 has 3 items. Factor 3 has 2 items. And factor 4 has 2 items. We will need to examine items in the same factors to see if they share commonality and decide the factor name. For example, for factor 1, we have complaint resolution, order and billing, and delivery speed, so we can name this factor customer service. For factor 2, we have e-commerce activities, advertising, and Salesforce image, so we can call it marketing factors. Factor 3 has technical support and warranty and claims, so we can call it technical support. Factor 4 has product quality and competitive pricing, and we can call it product value. The factor names should represent well the items measuring that factor. Component transformation matrix is usually not interpreted. Basically, it shows us the correlation among identified factors. In this example, we can note that this matrix does show some extent of correlations among factors, which brings up the question about the rotation method. Please remember that orthogonal rotation assumes factors are independent. We will run the EFA again using oblique rotation. We go back to factor analysis and make only one change on rotation option. We select direct oblique as the rotation method. Fortunately, SPSS does offer an oblique rotation method. Some other applications might not offer this option. We also add X11 back to the list. Let's look at the output. The eigenvalue, number of factors, and total variance extracted are the same. The script plot also looks the same. In this case, we do not have rotated components matrix. Instead, we have pattern matrix and structure matrix. We can see that the factor structure is also the same. X11 still has the cross-factor loading issues with factor 1 and factor 4. So we will remove X11 from the analysis and run it again. This is the output. We will examine the pattern matrix, which shows a similar results to Varimax solution. Factor 1 has X9, X16, and X18. Factor 2 has X7, X10, and X12. Factor 3 has X8 and X14, and factor 4 has X6 and X13. The only difference is that factor loadings for factor 2 are negative, but they still measure the same factors. The component correlation matrix also shows the correlations among factors. We can also note that this matrix is symmetrical. Again, if we are going to test the correlations among factors, the oblique rotation is a more appropriate method. But in many cases, both methods result in the same factor structure. And that is how to conduct exploratory factor analysis using the SPSS. Thank you, and bye now.